This is GCSE Physics. This is Particle Model Lesson 8, and this is a relationship between pressure and volume. Objectives: to record the equation of pressure and volume at constant temperature, then apply the equation to physical problems, and explain the relationship between pressure and volume at constant temperature in words. Okay, let's move on. Remember to pause at any point if you wish to make any notes. So first of all, temperature of a gas. So the particles in a gas are constantly moving. They move in random directions or with different speeds. So the random directions and different speeds is very important. And the temperature is related to the average kinetic energy of the gas. So the hotter a gas is, the more kinetic energy it has, the faster the particles within the gas will move. So the higher the temperature, more kinetic energy gives us higher speeds. So that's all really important if you want to get that down. Okay, let's move on. So pressure in a closed system / container, you can call it. A system is like a container full of gas, for example. So the pressure in a closed system is caused by the atoms of the gas or the particles colliding with the container walls. The forces from the gas, the gas atoms or gas particles, always acts at a right angle to the container wall. This force acting at a right angle to the container wall over a certain area is the pressure of the gas. Remember, pressure is force divided by area. We covered that in an earlier lesson. So that's how pressure is caused. Remember to pause if you need to make any notes. Let's look at a certain example then. So in this example, as you can see, the gas 1 and gas 2 are the same gas, the same amount of gas, but gas 2 has been compressed slightly. So if the gases are at the same temperature, comment on the volume and the pressure. So what do you think is happening compared to each other, comparatively? Okay, let's have a look at this. So gas 1, there's more volume, and if there's more volume, there'll be less pressure. Gas 2, there's less volume, so there's going to be more pressure. Okay, let's move on. So at constant temperature, the pressure of a gas is inversely proportional to its volume, and mathematically it looks like pressure, proportional sign, 1 over V, which gives us an equation, PV equals a constant, and we'll look at that again later. And we've also got P1V1 equals P2V2. So if you want to get that down, then I'm going to show you how to manipulate that in a moment. Okay, let's look at that. So as we said earlier, pressure is inversely proportional to volume. So what that means specifically, it means that if you change one thing, the opposite will happen to the other. So if we increased volume, the pressure would decrease. Okay. And if we decrease the volume, so if we made it smaller, the pressure would increase. And we can write mathematically, pressure is equal to a constant divided by volume. You should have done this in maths. If not, you will do. And we can say that PV is equal to a constant. Now, because of that, if you can't follow that, if you're not at that level, you can still do the questions. We've got an equation: pressure 1 times volume 1 must be equal to pressure 2 multiplied by volume 2. Okay, so pressure is obviously measured in, well, it's normally measured in pascals. It could be in kilopascals, as long as pressure 1 and pressure 2 are the same. You can't mix the units. So if one's in kilopascals and one's in pascals, you'll have to convert one. Same with the volume. It could be in centimeters cubed. It could be in meters cubed. Okay, as long as they're the same. So centimeters cubed and meters cubed. So we'll do some example questions. So I've got some, like a word fill exercise and a selection of graphs to show you a couple of graphs that can be asked about, and then we'll do some calculations using this equation. Okay, if you want to pause and have a go at this. Okay, let's look at the word fill first. For a fixed, let's say, for a fixed mass of gas at constant temperature, excuse my handwriting, The pressure of a gas increases as the volume of the container decreases. Again, the opposite happens. The pressure is inversely proportional to the volume. So next bit, select two, depending on how good you are at maths, this could be either really easy or not. So select the two graphs below that represent the relationship between pressure and volume for a fixed mass of gas at constant temperature. Remember, Professor pressure is inversely proportional to volume at constant temperature. That's this relationship on the left. So if we've got pressure against volume and it's inversely proportional, this graph would be correct, this one. Now the other graph, if we did pressure and put it against 1 over V, that's also correct. So in your exam, if you're asked anything like that, they're the graphs. If you're good mathematically, that should be very apparent anyway. Okay, let's do some equation stuff. Now, be very careful with these. Some of them are a little bit wordy. You get to have a think about what you're doing. And you might make a few mistakes, but there won't be mathematical mistakes. There'll be mistakes because of the wording of the question. So if you want to pause and have a go, I'll start with the first one. A sample of gas has a pressure of 500,000 pascals and a volume of 0.5 cubic meters. The volume is increased to 1.2 cubic meters, or meters cubed. If the sample of gas within the system stays at the same temperature, calculate the new pressure. So I'm going to start with pressure 1, volume 1 equals pressure 2, volume 2. And we want the new pressure P2. So to get P2, I need to get rid of a times volume 2. So to get rid of a times volume 2, I'm going to do the opposite of times and divide it on the other side. So that would be pressure 2 would be equal to P1 V1. And then I need to divide by volume 2. Then I just need to put the numbers in. So pressure 1 is 500,000, so 500,000 times volume 1, which is 0.5, divided by volume 2, which is the 1.2. And that will give us a pressure of 208,333 pascals. If you've written 208,000 or 208 kilopascals, that's fine as well. Rounded it up. Right, let's have a look at number 2. So a sample of gas has a pressure of 250 kilopascals and a volume of 650 centimeters cubed. The container housing the gas is reduced in volume and the new pressure reads at 700 kilopascals. Calculate the new volume. So unit-wise, the pressure is both in kilopascals, so that's fine, and the volume's in centimeters cubed. So that means our answer for the new volume will also be in centimeters cubed. So pressure 1, volume 1 equals pressure 2, volume 2. So we're finding volume 2. So we need to get rid of a times pressure 2. So the opposite of timesing is dividing. So volume 2 will simply be pressure 1, volume 1 divided by pressure 2. Then let's put some numbers in. So pressure 1 is 250 kilopascals times volume 1 of 650 centimeters cubed divided by pressure 2, which is 700. So you put that in your calculator. That gives us 232 centimeters cubed. Right, and the next one. So a sample of gas has a volume of 5 meters cubed and the volume is increased by 2 meters cubed. So that means our second volume, V2, is going to be 5 plus 2, which is 7 cubic meters. Okay, the original pressure is 0.01 megapascals. Calculate the new pressure. We can leave it in megapascals, that's fine. So pressure 1, volume 1 equals pressure 2, volume 2. So pressure 2 is going to be P1 V1. And then to get rid of the volume 2, we need to do the opposite of timesing, which is dividing on the other side. So pressure 1 is 0.01 megapascals times volume 1, which is 5, divided by volume 2, which is 7. Calculate that. And that's 0.007 megapascals. Hopefully that went okay. Right, I've got a bit of an extension question if you want to have a go at this one next. Pretty hardcore, this one. So if you want to pause and have a go, and then I'll take you through the answer. So a sample of gas has a pressure of 5 times 10 to the 6 pascals and a volume of 0.5 cubic meters. The pressure of the gas is increased by 1.5 times 10 to the 6 pascals. calculate the change in volume of the gas. So it's in standard form. If you've done standard form, it should be okay. If not, 5 times 10 to the power of 6 in a scientific calculator, I'll just start with this, will be 5. And then there's a button, times 10 to the power of. It's normally it's at the bottom of the calculator, and it looks like times 10 to the power of. And then 6. So that'll give you 5 times 10 to the 6, or 5 million. And if you're doing 1.5 times 10 to the 6, it'd be 1. Press the point button. Then 5. And then times 10 to the power of. So times 10x, power of 6. Okay, so if you wasn't sure how to put them in your calculator, that's how you do it. So I'm just going to rub them off, and let's have a look at the question. Apologies if you already knew that. So a sample of gas has that pressure and it's increased by that much. So let's do P1 V1 equals P2 V2. So let's find the second volume first of all. So the first pressure is simply 5 times 10 to the 6. Multiplied by its original volume of 0.5 cubic meters equal to pressure 2. Now it's not the 1.5, the pressure has increased. So we need to do 5 times 10 to the power of 6 plus 1.5 times 10 to the power of 6. So that gives us 6.5 times 10 to the power of 6 for the second pressure, multiplied by volume 2. Okay, so if we do 5 times 10 to the 6 times 0.5 and then divide by the 6.5, so let's just write that out. We need to get V2 the subject, so we need to get rid of the times. 6.5 times 10 to the 6, so we're going to divide, there we go, calculate that. And that gives us the new volume of 0.38 meters cubed, which is correct, but not the answer that we're looking for, because we want the change in volume of the gas. So the change in volume of the gas will be the original, 0.5, subtract the final. Or you could do final, subtract, but you just end up with a negative value, but it'd be the same, I imagine. So 0.5 cubic meters minus 0.38. which gives us a change in volume. I'm going to write delta V of 0.12 meters cubed. Hopefully you found that all right. If you got that right, then very, very well done. It's impressive. And if not, don't worry about it. And if you want to have another crack at it, just rewind, get a new sheet of paper, and off you go again. More practice, the better. Anyway, thanks for watching, and I'll speak to you soon.